Given given is 6-cylinder refrigerant 22 compressor. Yan, 29 revolution per second. 96.4 kilowatt refrigerating capacity. 28.9 kilowatt power requirements. The operating temperature of 5C, so sa evaporator. Condensing temperature is 30C. 3C liquid subcooling and 8C superheating. Cylinder bore 67 millimeter. Piston stroke is 57 millimeter. Then the clearance volume is 4.8%. Okay, yung cylinder, alam mo ba, may bore and stroke. Ang stroke yung yung length, di ba? Required, so sulat niyo yung required uli. This is the clearance volumetric efficiency if the clearance volume is 4.8%. Basta may malagay kayong given required then solution. B, the actual volumetric efficiency and C, the compression efficiency. Okay? Give laging required. Kailangan natin yung given required then solution para alam nyo yung sinosolve nyo. Solution, so figure, lagay natin kasi dyan ang magiging reference natin ng cycle. So at state 1, so that is 5C saturation temperature, which is 584 kilopascal, yung pressure niya. So sa pressure, mag-extend siya papunta dun sa saturation uh, region. So ang T1 mo is 5C plus 8C is equal to 13C. Kasi nga yung ano mo, saturation mo is 5C, meron kang 8C na superheating. So ang actual mo na T1 is 13C. Then from refrigeration properties ng refrigerant 22, so H1 is equal to 413.1 kilojoule per kilogram. So B sub 1 is with 43.2 liters per kilogram. And S sub 1 is 1.7656. Zero na yata kasunod yan, kaya di na sinama. Okay? Huwag niyong i-round off. Yung mga S1 is 2. Diba? Pangit yun. So, lagi kayong may allowance sa enthalpy. 413.1. Huwag mong 413.1, ginawang 413, binuo mo. Laging may isang decimal place dyan. So, V sub t is 43.2. Pwede din 43.24, basta ganyan. Sa entropy, mahaba yan. Sa table kasi mahabang entropy. Tapos hanggang 6 decimal places yan. Okay. At state 2, 50C saturation temperature. Yan. Yan. Andito yan. Temperature niya is 50. Pero ano yung pressure? So pressure, hanapin mo sa table niya. 1942 kilopascal. So yan ang pressure na yan. At 2 to 3. So that is S1 is equal to S2 kasi isentropic. So therefore, H2 is equal to 444.5 kilojoule per kilogram and B sub 2 is 14.13 liters per kilogram. Procedures for pagkuha niyan, values, so back to basic kaya. Yeah? Yung pagkuha ng mga properties. Quality. Yan. So, sa tables. So, dapat marunong na kayo. Hindi na kailangan ulit-ulitin natin yan. Okay? So, at state 3 and 4, at 47 saturation. 47 is subcooled. So, 50 minus 3 is 47. Yan galing yung 47. Subcooled siya kasi 50 sa lumabas dito, pagdating sa dyan ang 50. Pagdating dito, nag-minus siya ng 3, kaya 47 at sa T3. So, this is now, kung naman properties, normally kinukuha yan, siyempre yung saturation properties. So, S sub 3 is equal to S sub F, 3, S sub 4, or S sub F dyan, at that temperature. Okay? Is 259.1 kilojoule per kilogram. Temperature, huwag kayo gagamit ng pressure. So, yan yung mga enthalpies. So, now, so meron na kayong value. A is equal to the clearance volume efficiency is N sub V is 100 minus C times B suction over B discharge minus 1 is equal to 100 minus C times B sub 1 over B sub 2 minus 1. So, N sub V is equal to 100 times minus 4.8 times 43.2. Huwag na tayong babalik sa previous slide. Alam nyo na yung B1, B2, kinuha natin yung value. Okay? 43.2 over 14.13 minus 1 is 90.1%. So, yan yung unang required. Letter B, compression displacement. Ano yung pangalawang required? Balik na pala tayo. Actual volumetric efficiency, tapos compression efficiency. Okay? So, actual is, ito yung formula. Yan. So, the compressor displacement rate is V sub D is 6 cylinder times 29 revolution per second times the span times 0.067 squared over 4 cubic meter per cylinder per revolution. Yan ang unit niya ng isang cylinder. 6 cylinder siya. Okay? So 0.057 is stroke. Ito yung bore. So this is 67 mm, ginawa mong meter. So ito naman, 57 mm, ginawa mong meter. So nawala yung equation. Lagyan yung lalagyan ng equation. Dito lang nawala kasi nakopy lang ito sa libro. B sub D is equal to 0.03497 cubic meter per second is 34.97 liters per second. This is number of cylinder times speed times volume. B pi D squared N over 4. Diba? Yun yung equation niya. Okay. Now, the actual rate of refrigerant flow is Q is equal to M times H sub 1 minus H sub 2 is ang formula. So, M is equal to Q 96.4 kilowatt over 413.1 minus 259.1 is 0.6260 kilogram per second. So, di ko na basahin yung units kasi consistent naman yan. Yeah? Now, the actual volumetric flow rate of the refrigerant measured at the compressor suction is P sub 1. Is equal to 0.6260 times 43.2 is 27.04 liters per second. So, yun. So, the actual volumetric efficiency is then N sub B is equal to B sub 1 over B sub D, which is the volume flow rate entering compressor divided by displacement rate of compressor times 100% is 27.04 divided by 34.97 times 100% is 77.3%. Okay. Letter C. The compression efficiency is the isentropic work of compression divided by the actual work of compression. So the latter is, so the actual work of compression is W prime is 28.9 kilowatt. So that N sub C is equal to isentropic work of compression divided by the actual work of compression times 100%, which is now M times S2 minus S1 over W prime times 100% is 0.6260, ito pa rin, times 444.5 minus 413.1 over 28.9 times 100% is 68%. So, yan yung mga answer nyo. Okay, hindi ko na nilagyan ng answer. Yan ang answers. Okay? Required. Next. Compressor discharge temperature. So, plotting naman siya. If the discharge temperature of the refrigerant from the compressor becomes too high, it may result in the breakdown of the oil, evaporation, causing excessive wear or reduced life of the valve, causing valves, particularly the discharge valve kasi doon yung mainit. In general, the higher the pressure ratio, the higher the discharge temperature. But the properties of refrigerant are also crucial. So figure 13, ito yung discharge temperature following isentropic compression from saturated vapor at 0C. Yan. Ito yung mga discharge temperature, condensing mo, tapos pressure mo. So, ayan yung mga temperature. Magating dito, laki na. Figure 13 shows that the discharge temperature for your pore refrigerant following isentropic compression from saturated vapor at 0C to various condensing temperature. Refrigerants 12 and 502 have low discharge temperature and have low, while refrigerant 22 experience higher temperature. So, pag kailangan ng magmatas, so pwede kang, pag hindi pwede to, so dito ka mag-change ng refrigerant. So, ito na application ng refrigerant 12 and 502 at low discharge temperature. So, the highest temperature of the four refrigerant shown is ammonia. Ammonia compressors are equipped with water-cooled head. So, the water lines are visible on the compression shown in figure 1. Yan. Next, capacity control. If a refrigeration system is operating in a steady state mode and the refrigerant load decreases, the inherent response of the system is to decrease the evaporating temperature and pressure. This change in the evaporator condition results in reduced compressor capacity, which ultimately matches the reduced refrigeration load, and the reduction in evaporator temperature may be undesirable for several reasons. In air conditioning, the coil may collect frost and block the airflow, further reducing the evaporator pressure. Stored pressed good and many other products may be damaged by low temperatures. If the evaporator chills a liquid, the liquid may freeze and burst a tube in the evaporator. Yan, kailangan ng capacity control. So several methods are commonly used to reduce the compressor capacity. One, in cycling, the compressor stops and start as needed. Cycling, zero on off, on off, on off. The method works well in a small system. Number two, back pressure regulations throttles the suction gas between the evaporator and the compressor to keep the evaporator pressure constant. This method gives a good control of the evaporator temperature but is inefficient. Number three, bypassing the discharge gas back to the suction line usually affords precise capacity reduction, but the method is inefficient and the compressor often runs out hot. A prepared bypass circuit delivers the discharge gas that is bypassed back to the entrance of the evaporator. Number four, another method is cylinder unloading on a multi-cylinder compressor by automatically holding the suction valve open or diverting the discharge gas from the cylinder back to the suction line before compression. So next topic, as next compressor is the rotary screw compressor. Yan, ang ganda ng kulay. How the screw compressor function? So this is a cross-sectional view of two principal rotating element of the screw compressor is shown in figure 14. Ito yung principal element, rotors, female and male rotors. Screw type. The male rotor with 4 lobes, yan, apat, ito yung lobes, is shown on the right, drives the female rotor in a stationary housing. Figure 5 shows an exploded view of the major parts of complete compressor. Pinion gear, male rotor, ito yung importante yan. Female rotor and male rotor. Ito, transmission na yan. Bearing, support, viscosil, bearing, yan. Ito yung mga main element of screw compressor. So the refrigerant vapor enters one end of the compressor at the top and leaves the other end at the bottom. Ito yung air. Sabi dito at the top. Okay? Sige. Basta yung sabi ito, refrigerant vapor enters one end of the compressor at the top and leaves the other end at the bottom. So at the suction position, bakit air? Taas sa taas. Yung area, ito sa loob. Loob tayo. At the suction position of the compressor, a void is created in which the inlet vapor flows just before where the interlobe space leaves the inlet port. The entire length of the cavity or gully is filled with gas. So as the rotation continues, the trapped gas is moved circumferentially around the housing of the compressor. So further rotation results in meshing of the male lobe with female gully, decreasing the volume in the cavity and compressing the gas. At a certain point into the compression process, the discharge port is uncovered and the compressed gas is discharged by further meshing out of the lobe and the gully. In the packaged water chiller shown in figure 16, the screw compressor is just to the right of the control panel. Ito. Asan yan? Ito is chiller. Ito yung compressor. Okay. Right. A water chilling package that uses a screw compressor. Ito yung chilling, kasi condenser yan, chilling tube. Okay. So, showing is relatively small size compared with condenser and water chilling evaporator at the bottom. The vessel below the control panel is the oil separator. Ito, a standard component in screw compressor system. Yan, may mga diagram yan. Makita mga oils, equipment, oil parts. Now, performance characteristic of screw compressor. Yan. At a certain point in the compression process, the discharge port is uncovered. This point is a function of the design of compressor and establishes a built-in volume ratio of the compressor. This ratio has a corresponding built-in pressure ratio associated with it, and any compressor has its best performance at a certain pressure ratio. Yung pressure ratio, built-in volume ratio. So, ang best performance na siyempre yung highest efficiency andyan. So, dito, yung 2 point built-in ratio na 2.33, so andito sa 2.5 pressure ratio. Di ba? Okay. Figure 7 shows curve of compression efficiency for several compressors of different built-in ratio. So, normal operation of most refrigeration system occurs over a range of pressure ratio as the condenser and evaporator condition change. So that a screw compressor does not always operate at peak efficiency. The peak efficiency are quite high. However, there is little sacrifice of efficiency if the pressure ratio does not change radically. Next, capacity control sa screw compressor. So many screw compressors are equipped with a sliding valve for capacity control. It is in the housing of the compressor and can be moved actually, what tayong picture, as the valve is open. It delays the position at which compression begins. The capacity can be modulated down to 10% of the full capacity, although there is loss of efficiency in the capacity reduction. Wala tayong makuha picture pa sa mga next revision na lang ito. Next is the main compressor. Yan. So this is the picture of main compressor. Andyan siya. Ang daming equipment yung control. Okay. So main compressor, ito itsura niya. Laki lang equipment. No, parts lang siya nun. So two basic types of main compressor sa dalawang klase are the roller or single vane. Isa lang. And the multi-vane type. Roller. Ito multi-vane. Ito maraming yan, vanes. Yan, marami. Okay. Vane compressors are used mostly in domestic refrigerators, freezers, and air conditioners, although they can also be used as booster compressor and the low pressure portion of large multi-stage compression. So in roller type, figure 18 and 19, the center line of the shaft is the same as the center line of the cylinder. So the center line of the shaft, however, is located eccentrically on the rotor so that the rotor revolves. It makes contact with the cylinder. So the roller type compressor has a spring loaded divider which separate the suction and discharge chamber. Ayan, spring. So the formula for the displacement of the roller type compressor is D is equal to pi over 4 times pi squared minus b squared times L times rotative speed in cubic meter per second. This is equation 10, where A is equal to cylinder diameter in meter, B roller diameter in meter, L is the cylinder length, and the rotative speed is in revolution per second. Now, in multi-vane compressor, ito, the rotor revolves about its own center line, but the center line of the cylinder and the rotor do not coincide. So the rotor has two or more sliding vanes which are held against the cylinder by centrifugal force. So yung 2 vanes and 4 vanes. So for the 2 vane compressor in figure 20, the displacement per revolution is proportional to twice the cross-hatch area. For the 4 vane compressor, the displacement per revolution is proportional to 4 times the cross-hatch area. Yan, up to a certain point, then the displacement is greatest on the compressor with the largest number of vanes. So, in the two types of rotary compressor shown here, no suction valve are needed. And since the suction gas enters the compressor continuously, gas position is at minimum. Next is the centrifugal compressor. Yan. Andyan yung centrifugal yan sa loob. Saan na ba yun? Yan. Piring yan eh. Ito. Yan. Yung motor. Ulit lang. Ito yung compressor. Yan. Ito yung bearing. Ito yung motor. Yan. So, the role of centrifugal compressor. So, ito yung centrifugal compressor system. Mga water chiller. Centrifugal chiller. The first commercial centrifugal compressor used in refrigeration system was promoted by Willis Carrier in 1920. Since then, the centrifugal compressor has become the dominant type of compressor in large installation. Okay? Ulitan ko lang dot, makaduling. Centrifugal compressors serve refrigeration system in the range of 200 to 10,000 kilowatt of refrigerating capacity. Evaporating temperatures in multi-stage machines may extend down to the negative 50 to negative 100 degrees C range. Although one of the largest uses of the compressor is for chilling water to about 6 to 8 C in the air conditioning system. So a cutaway view of complete refrigeration system using centrifugal compressor is in figure 21. System kasi kasama yung condenser and evaporator. Yung expansion valve, andyan na sa loob. Yung expansion valve yata yan. Yung, tapos, motor, compressor, so andyan na. System, complete system of refrigeration, lalabas dyan is chilled water. Operation. Centrifugal compressors are similar in construction to centrifugal pump in that the incoming fluid enters the eye of the spinning impeller and is thrown by the centrifugal force to the periphery of the impeller. Thus, the blade of the impeller impart a high energy to the gas and also build up the pressure. From the impeller, gas flows either into diffuser blade or into a volute, where some of the kinetic energy is converted into pressure. The centrifugal compressor may be manufactured with only one wheel if the pressure ratio is low, although the machines are generally multi-stage. Centrifugal compressors operate with an adiabatic compression efficiency of 70 to 80%. Yan, yan. 70 to 80%. Dito sa mga reference yung mga typical values ng yung efficiency. Hindi ka na magtatanong. Magtanong ka, hindi rin alam. Okay? Next, plus gas removal. Plus gas removal, ginagamit to between the compressor. So, meron tayo sa mga gas compression cycle, meron tayong intercooling. Dito meron din. Okay? Sa mga refrigeration compressor. Centrifugal compressor with two or more stages involves the use of plus gas removal. Plus gas can be removed by partially expanding the liquid from the condenser, separating the plus gas and then recompressing the gas instead of dropping its pressure further. So, plus gas removal increases the efficiency of the cycle and is conveniently achieved when two or more stages of compressions are available. Yan. So, from raw compression, tapos dito, discharge siya, papasok siya sa intercooler, then, pasok dito, saturated naman siya, so liquid from condenser. So, tatapik din natin to sa ibang discussion. And then, 4, 5, so pasok na sa condenser. Plus gas kasi dito, papasok niya as vapor. So, cycle nito is papakita sa isang topic. Next, performance characteristic. One choice of coordinates for presenting the characteristic is shown in figure 2. This is per characteristic curve. So, discharge to suction pressure ratio, flow rate. This is the performance of a centrifugal compressor sa mga brochure makikita nyo doon. Ang lagi natin hinahanap is siyempre yung high efficiency. Yan. By model, may makita kang by model. So, ano yung sa model na mataas yung efficiency, yun ang selection mo. So, the discharge to suction pressure ratio versus the flow rate. Yan, ang figure na to. The graph shows the performance for several different compressor speed and ISO efficiency line of constant efficiency. No performance curve are shown to the left of the source line. Ito, wala na to. Kasi out of ano na yan. Out na yan. So, dito lang tayo mag-concentrate based doon sa speed. So, sa model mo, meron siyang ilagay itong speed. Yan ang performance. At different speed, sa iba-iba yung performance. So, naalala niyo yung mga pumps. So, pumps, ganun din. So, kung ano yung theory ng pumps, ganun din dito. So, now, tip speed to develop pressure. So, nasa refrigeration tayo, baka kasabay lang nito yung fluid machinery. Okay? So, a rough estimate of the tip speed of the impeller can be made using several fundamental relationship for turbo machinery. Yan yung fluid machinery niya. The torque the impeller ideally imparts to the gas is T is equal to M times B sub 2T R sub 2 minus B sub 1T RT. So, where T is equal to torque, M is the mass rate of flow in kilogram per seconds. English units, pwede rin. V sub 2D is the tangential velocity of the refrigerant leaving the impeller. So, wala pa tayong figure dito ng impeller. So, wala nga. Okay? So, next revision na lang. Future. So, ano mga kulang? Okay? R2 is the radius of exit of impeller. V sub 1T is the tangential velocity of the refrigerant entering impeller. R sub 1 is the radius of inlet of impeller. Okay? So, visualize nyo lang to. Alam nyo naman itong sa fluid machinery, di ba yung impeller, may mga velocity, tangential velocity. So, check nyo lang doon. Okay? So, ngayon, wala pa tong figure kasi sa dami ng subject na ginagawa. So, if the refrigerant enters the impeller, ano, galaw. In an essential radial direction, the tangential component velocity of V sub 1T is equal to 0. So, radial nga siya. So, initial velocity mo pagpasok is 0. Tangential, ha? And so, the torque is M times V sub 2T RT sa compressor. Sa turbine, baliktad naman. Okay? Ang ano mo, torque mo is, subscript niya is 1. Okay. The power required at the shaft is the product of torque and the rotative speed. So, P is equal to T times omega or W. M B sub 2T R sub 2W or omega. So, W na lang. Where P is equal to power in watts. W is rotative speed radians per second. Watts to kasi yung velocity mo is meter per second, radius mo is meter, mass mo is kilogram per second. So, pag multiply mo siya, magiging watts. Okay? Kung gusto mo gawing kilowatts, divide mo ng 1,000. Yeah. At least at very low refrigerant flow rates, the tip of speed of the impeller and the tangential velocity of the refrigerant are nearly identical. Therefore, R sub 2 W is equal to B sub 2T and P is equal to M times B sub 2T squared. Sabi niya, at least. Okay. So, another expression for the ideal power is the product of the mass rate of flow and isentropic work of compressor. So, P is equal to M and delta SI times 1,000 joules per kilojoules. So, equating the two expression for power, expression 14 and 15. So, B sub 2T squared is 1,000 times delta SI. Yan. So, although equation 16 is based on some idealization, it can provide an order of magnitude estimate of the tip speed and can also show important comparison. Yan. So, itong formula to, makita nyo rin to sa fluid machinery, saka sa steam turbines. Yan. So, common to, di ba? Delta S times 1,000. Basta, yan. Makukuha mo yung velocity niya. Okay. So, next, sample 2. Calculate the speed of the impeller tip in order to compress the following refrigerant from saturated vapor at 10C to pressure corresponding to a corresponding temperature of 30C when the refrigerant is A, refrigerant 11, and B, ammonia. So this example, yung sa topic na itong tip speed, kung gusto mo na mag-design ng blade, sa blade, makuha mo yung velocity, makuha mo yung mga iba pang parameters noon, may mga table naman yung ano na yung mga thickness ng blade, impeller, ganyan. So, ito yung purpose nito. So given evaporating temperature of 10C, condensing temperature of 30C, required speed of the impeller tip for A, refrigerant 11, and B, ammonia. So solution, A, in the isentropic compression of refrigerant 11 from saturated vapor at 10C to a saturated condensing temperature of 30C, we have delta SI is equal to 406.7 minus 393.9 or 12.8 C. So, kinuha ko lang itong format niya sa libro. Yung delta SI, so, magagawa ka ng saturated vapor 10C, so saka natin ipakita sa revision na lang uli. So 10C saturated, makuha mo yung 393.9. Tapos isentropic mo, then saturated condensing temperature kunin mo doon. So kung para sa table, sa table kasi nakalagay na saturated condensing temperature. Minsan wala, kunin mo yung pressure, equivalent niya. So then doon ka sa pressure kukuha. Isentropic sa superheated na table ng refrigerant 11 o sa chart, sa graph. O sa graph, medyo mahirap magtansya. So, sa table na lang. So, that is 406.7. So, difference is 12.8. So, the tip speed is B sub 2T is equal to the square root of 1,000 times 12.8 is 113.1 meter per second. Okay. So, check nyo yung paano pag-solve naman ito ng English units. May conversion doon. Kasi nga, BTU per pound yung ano mo doon, di ba? So, meron kang 778.16. Gagamitin mo dito para magamit mo makuha mo yung velocity in feet per second. So, letter B for ammonia. So, delta SI is equal to 1560 minus 1472 or 88 kJ per kilogram. Yung 1472 is saturated. Then, kumuha ka ng isentropic, punta ka ng 30C saturated condensing temperature, makuha mo yung 1560. Now, the tip speed is B sub 2T is equal to the square root of 1,000 times 88 is equal to 297 meters per second. So, yun ang procedure nito. So, di na masyado saka na. So, next, ano natin, ano tong mga expand to. Okay. Tip. Wait. Yan. 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 So, choice of impeller and refrigerant. There are two crucial impeller dimension are the wheel diameter. So makita mo sa mga curve, kahit sa pump, di ba? Mayroon ng wheel diameter. Yan. Kasi wheel diameter, gawa na yon. Pipili ka na lang ng kung ano yung diameter doon, di ba? Hindi ka mag-interpolate. Mag-interpolate ka, ipapagawa ka ulit ng bagong impeller. And the width between impeller faces. The designer of a centrifugal compressor system must select a combination of this dimension along with choice of refrigerant. The magnitude of a wheel diameter is heavily dictated by the discharge pressure that must be achieved. Because for a given rotative speed, a large wheel diameter will provide a higher tip speed, which result in higher pressure ratio. So, sa ibang topic na yon, sa fluid machinery yon. Pero hindi rin yung inaabot sa fluid machinery kasi puro yon water. Diba? Pero yung mga theory niya, ganun din. Pagdating mo sa steam, sa refrigerant, steam and refrigerant, the same ang theory naman dito sa sinaskas natin kasi vapor. Yung bang may change of phase. Yung iba, wala. Yun nga, yung sa water lang. Tatlo kasi ang sa fluid machinery, di ba? Yung steam, water, and air. Okay. So, halos maraming topic doon sa fluid machinery is for water. Yung turbines. Next, another decision of the designer is the width of the passage in the impeller. To increase the capacity, increase the width between the faces of the impeller, which of course also increases the power requirement. Dito kasi dumadaan yung refrigerant mo. So, sa ibang subject na yan. Advanced topics. Next, surging. Figure 22, yan, shows no performance to the left of the surge envelope. Although the classic performance of backward curve blade pump, fan, and compressor would be shown by the dashed line in figure 23. As the refrigeration load drops off and the flow rate decreases from point A, the performance rises up the pressure flow characteristic to point B. Further decrease in flow rate sends the operation to point C where the pressure ratio capability of the compressor drop. The drop in pressure is due both to the inherent characteristic of the backward core blade turbomachineries and to the fact that flow separation begins occurring at the blade. Flow separation, hiwalay siya. So dito ang the best. Huwag ka dyan sa source. Capacity control. The two most efficient and most widely used methods of capacity control are one, adjusting pre-rotation vanes at the impeller inlet, and two, varying the speed. Two methods that are not efficient and not widely used are varying the condenser pressure and bypassing the discharge gas. The latter was mentioned as a means of preventing surge and is sometimes combined with the pre-rotation vanes. So, ang topic natin dito sa ngayon is basic. So, di pa natin masyado ma-discuss to. So, advanced topic sa mga seminars nyo lang tingnan to. Mga sa operation ng refrigeration system. Ito rin. How the various types of compressors share the field. So, saan ginagamit? The four types of compressors studied, reciprocating, screw, bend, and centrifugal all have somewhat different qualities so that each type has found a sphere of application where it has advantage over the others. A reasonable accurate statement of where the compressor are used can be based on their refrigerating capacity, yung range. Reciprocating compressors dominate from very small refrigerating capacities to about 300 kilowatt. Centrifugal compressors are most widely used for unit nights in 300 to 500 kilowatt capacities and competes against large reciprocating compressor and against small compressor. The vane compressor competes against the reciprocating compressor primarily in the market for domestic refrigerators and air conditioners. Okay? Pag maliliit, ito sa yung mga reciprocating. Pero pag sensitive siya sa vibration, so meron tayong mga screw. Centrifugal. Centrifugal naman is sa compressor o sa chiller, yung power consumption mas mababa compared sa reciprocating. Kita naman yung yung power kilowatt per ton ng chiller. Okay, so this is the end of natin, compressor. So ito yung sa compressor, nandiyan sa window type na aircon, di ba? Okay. Thank you very much. End of topic. Then close.